Right, now we're on to the traveling salesman problem, which is basically the last thing we really need to learn before looking at some kind of examples and exercises. So the traveling salesman problem, we've spoken about this. It's about the saleswoman who wants to visit a number of locations, preferably each one only once, and then return to her office, which we know as a Hamiltonian circuit. Obviously, she'd want to minimize either cost or time or distance, etc. So, Hamiltonian circuit of minimum weight. However, up until now, no algorithm has been found for finding a minimum solution. So there's lots of money in this if you are wise and clever enough to seek out this algorithm. Basically, you could just check every single possible route to find a solution, but this is a huge task. I mean, of course, you could get a computer to do it, but hours and hours and hours of computer work checking every single possibility, especially when there are quite a number of, it's quite a big graph. An example would be, flights. There's a huge number of flights, for example, in the States out of all the airports. And so it's amazing when we do probability and we look at combinations and permutations, how many possibilities there are. It just becomes too huge. So in order to reduce the time it takes in order to check every single one, we settle for finding what we call a very good solution using one of the algorithms that has been designed. So basically, we don't know if it's the best one, but we settle for a very good one. Using this, we're going to find a very good solution, but one of the algorithms that we've already designed, we're basically going to find a range into which the solution has to fall. Now, this might sound silly, but basically it allows for people to plan. Will you have enough time or money or petrol, etc., to do the trip? Basically, we need to know, well, what's the absolute minimum it could be and what's the absolute maximum it could be. Because if you have more money than the maximum, then of course, it's definitely possible to arrange the trip. If you have less money than the minimum, there's absolutely no ways in the face planet you can do the trip. The only problem is if you have an amount of money somewhere in the middle of the minimum and maximum, you actually then have no conclusive proof. So you'd have to find a good solution by inspection. So let me just show you how this works. So basically what we need to first look at is we need to find something called a lower bound. Now the reason why it's called a lower bound and not a minimum is that by definition the word minimum implies that you can achieve it, whereas a lower bound might not actually work. So it's the absolute minimum theoretical weighting for which a route could hypothetically exist. The lower bound might not even be possible, and you'll find in most of the questions we do, the lower bound actually, there's no ways the Hamiltonian circuit would work. But at least we know that there's no shorter route than this one. Now the upper bound is the weight of a route that definitely does exist. So basically, if you can find a route that definitely does exist, surely the best solution has to be that or less than that. And so an upper bound is always achieved. It's a route that does exist, and basically anything below that would be even better, but this one definitely exists. So there might be routes with larger weight, and there might be routes with smaller weight, but at least you know that that weight is achievable, and so aiming for anything less than that would be an improvement. Basically, then what happens is, once you find a lower bound and upper bound, you try and find a good solution that lies somewhere between the two values. And obviously, unfortunately, this is trial and error because no algorithm exists yet. The narrower you can get the range between the lower bound and the upper bound, obviously the better, because then, there's less room for kind of error type of thing. So we need to look at two things in this video. How do we find a lower bound and how do we find an upper bound? Now, finding a lower bound is basically like finding a spanning tree because you need to be able to go to every single vertex. So when we determine a lower bound, before I say that, the only thing with the spanning tree is, remember, there are no circuits in a spanning tree. So a spanning tree can't possibly form a circuit. So we're almost going to form a spanning tree, but like with a twist at the end, in that we want to have a circuit. But basically still, it might not actually form a circuit that works. So basically, when we determine a lower bound, you're always given a vertex that is initially left out. Now, depending on which vertex is left out, the lower bound will vary. So basically, you could take a graph like this one given, and you could find a series of lower bounds by each time leaving out a different vertex and then using the algorithm and finding all the lower bounds. Now, obviously, the highest of the lower bounds is the one you're actually interested in, because no solution will exist below the lower bound. And so the higher the lower bound, the more accurate your range would be, if that makes sense. So in the example below, a salesperson, let's say, leaves her office at F. So there's her office at F, and she wants to visit all the stores in the Western Cape, and basically the numbers are the distance between the stores. So we need to remove any vertex from consideration, and in an exam I would tell you which vertex to remove, because otherwise I have to mark all of these different solutions. So in this case, let's remove vertex D. Now when we say remove vertex D, we basically mean that anything connected to vertex D I'm not going to use. So I'm going to completely ignore all of those edges that go into vertex D and think of the rest of the graph as the only one that exists. So that's step 1. Step 2 is now create a minimum spanning tree for the rest of this graph, either using crystals or prims. So basically, let's cross these out so we don't get confused by them. So D doesn't exist, and all those edges going to it don't exist. Now, so minimum spanning tree, I much prefer crystals, because then I can just go crazy. So basically 30 is the smallest edge, and then I've got 245, so the order in which I selected them wouldn't matter, but now that's useless, and then 65 would be the shortest, and so that's useless to me. That would be my spanning tree. Either via crystals or via prims, you would get the same spanning tree. So that's step number 2. Now, so we've got our spanning tree in place. Now what we're going to do is they want you to connect the removed vertex, which in this case is D, to the spanning tree using the 2 shortest lengths to connect the vertex to any 2 points on the tree. So basically either this 80, 55, 80, and 55 again, any 2 of those have to be included now to form the lower bound. Now obviously you pick the shortest, so 55 would be the shortest and 55 would be the shortest. And these lengths added together would be the lower bound if you removed D. So if I added this correctly, I got 295 as the lower bound, considering D as the deleted vertex. Now, just for fun, let's try exactly the same thing, but let's remove B. So and let's see how it differs. So if B was disconnected, that means everything going to B gets ignored, and I would find the spanning tree for what's left behind. So if I use crystals, it would be 30, 45, either the 55, so order doesn't matter, remember 55, and there we go, I'd be done. That I'm pretty sure is my spanning tree. I'm just looking at it. And then I now need to reconnect B using the 2 shortest lengths, which would be 45 and 55. Now, just visually, you can see that they're different. For example, this 55 was not used and now it's used. This 65 was used over here and now it's not. And so I'm definitely going to get a different answer. Now again, if I did this correctly, I get 285. So this gets me a smaller lower bound. Now 295 is a better lower bound because there's nothing possible smaller than a lower bound. Now if you look at this, are these lower bounds either of them achievable? Definitely not. If you started at F, for example, here, and these blue highlighted lines were my options, I could go out, and then I couldn't go anywhere. Or I could have gone to A, but then I can't go anywhere. So these are definitely not achievable. And again, if I start at F, if I go along the 55, I go up. Now, either one of these options which I take, I can't get out again. Or I suppose maybe I could take B. But even if I went B, down to E, and back to C, and then out to A, I still can't get back to F. And so notice that neither of these lower bounds are actually producing a solution. But at least you know that there is no possible solution that is smaller than 295 in this particular example. So just for argument's sake, if you only had enough time to I don't know, drive 280 kilometers that day, you know that it's completely not possible for you to do, because an answer has to be above 295. Or if you only have enough money to cover 280 kilometers for petrol, there's no ways you can do this trip. So it just allows you to rule out whether it's possible or not. Okay, so that is finding a lower bound. The next one is determining the upper bound. Now this is a new algorithm, so we've learned 3 this year. We've got Prim's, Kruskal's, and now this is called the nearest neighbor algorithm. Now I actually really like this name because it's the only way that allows me to remember what to do. So the best idea would be to try and make an upper bound as close as possible to the lower bound to basically ensure that that range is quite small. So when finding an upper bound, it has to be given which vertex you're going to start the process at, because otherwise I have to mark all different options. Now, again, depending on which vertex you start at, your upper bound is going to vary. So a good idea would be to try and start at all of the vertices and find, in this case, 6 upper bounds, and then the lowest of those upper bounds is the best one to use, because you know that that one's possible, and so it's the lowest solution so far that you know exists. So basically, I will tell you, but you can pick an arbitrary vertex and you call it the current vertex. So this is given to you. So in this case, we're going to use F, which makes sense because that's her office, and so she has to start there and she has to end there. Now basically, we need to now find the edge of least weight that connects F to a new vertex in the tree. Basically, you always connect the current vertex to its nearest neighbor. That's why I like the algorithm. So basically, the name of the algorithm basically. So who's the nearest neighbor to F? And that's D. So that would be my first selected one. Now this is not like Prim's, because if I've gone F and I've gone to D, I'm trying to make a circuit. And so I don't want to now bop all over the place and now connect F to example E. No. This new vertex, which is now D, becomes known as the current vertex. So from there, can you find the least weighted edge that connects this vertex to a vertex that's not yet visited? And then that will become the current vertex. Because remember, you're trying to find a circuit. So I'm basically just kind of walking along and finding the closest neighbor and drawing a circuit, really. So who's the closest neighbor to D is now C. Okay, now C is the current vertex. So far I've got F to D, D to C. Now who's the closest neighbor to C? The nearest neighbor would be A. And so basically you kind of make this worm as you go. So C, F to D, to C, to A. Now who's the nearest neighbor to A? Now here's where you just have to be a little bit careful. Sometimes it's quicker to go through an already visited vertex and out to an unvisited vertex than directly there. And that is completely allowed. So remember what I said, it's like finding a Hamiltonian circuit, except sometimes it's not a Hamiltonian circuit. Because if you go through a vertex twice, it's technically not called a Hamiltonian circuit. But if you're trying to minimize something, why not go back and then out again? So for example here, maybe it's easier to go 30 and then out to B. Well, that would be 75, and I can see 65 is actually better. So no, in this case it doesn't work, and 65 is better, but keep your mind open to that. So basically you're repeating all of this until all the vertices are visited, and then you go back to where you came from. So B down to D, up across to A. Now B is the current vertex. So again, you could go into C and then out again, but that doesn't make sense here because 55 is the nearest unvisited neighbor to B. So now we're there and we've visited all the vertices. So once we've visited all the vertices, basically you just go home as fast as you can. Once you've visited all your cities that you needed to go to, should you just go home? So what's the fastest way home? Again, the fastest way home could mean you go through a visited vertex and then out again, but here our fastest way home is straight down. Now, this upper bound, this circuit works. That definitely works. And so it is an achievable route, but there might be something better. So just out of interest, if I added this correctly, I got 225 kilometers. So that's quite a significant bit above our lower bound. So our lower bound was 295 was probably the best. So actually maybe it's not too bad. So 200, yeah, it's only about 30k. So that's actually quite nice and narrow, actually. So basically we're finding a Hamiltonian circuit. Just as a general guide, if the last few edges you added are about the same length as the first few, then your proposed route is pretty good. So this particular proposed route was fairly good. We avoided the 95s and the 80s. If your last few edges that you add land up being quite a lot bigger, then generally you can find a better route by trying to avoid those. And then once again, I've just written there, be aware that the shortest way to connect to an unvisited vertex might actually be through a visited vertex. So let's look at example 2. This graph below shows the hostels in the national park and the paths joining them, the number on each edge in the kilometers, starting at G. Now, I know I made a typo in the notes because I think this said N. But basically starting at G, which is here, it says, can you determine the upper bound using our nearest neighbor algorithm? So our upper bound is going to be G definitely to I, because that's the closest. Now, who's the closest neighbor to I? The closest neighbor to I will be H. Now, the closest neighbor to H, remembering that it might be helpful to go back to G and then out, but I don't think so. I think the best thing is now to go to J. Okay, now here's the thing. Once we're at J, the only unvisited vertex is K. So either I need to go 7 back to H, and then out, now that'll be 17, or I need to go 7 and 13, which would be 20. So it definitely looks like re-traveling that 7 and out to the K would be better, and now I need to go home. Now I would definitely take the 13 home because there's lots of other routes. I could have done 13 and 4, but that's 17, so that's longer. I could have done 10 and 5, which is 15, but that's longer. And there are many other routes around there, but they're definitely longer. And so this would be my nearest neighbor. So if they said, what's the upper bound? They didn't ask for the route. They normally do ask for the route. So 3 plus 4 plus 7 again plus 10 plus 13. Now, if I didn't make a mistake, I get 44 kilometers. Now, can you find a better route by inspection? Now, what actually caused our problems here was this idea of going 7 and 7 again. So can we avoid that? So just for example, there might be lots of ways I could look at this. So can I go 3, and then could I rather go 7, 7, 10, 13? Okay, now that's an option. There are other options. So this is not the only one. Now that would be 3 plus 7, that's 10, 17, 27, 40. So that's better, and as long as it's better, it's going to be a good route. So G to I to J to H to K and back to G. And again, if I did my sums correctly, that'll be 40 kilometers. So that makes a lot, possibly more sense. And you can see where it's better for you to like kind of cut some corners because you can see what went wrong. And the doubling the 7 was kind of a silly thing, whereas this made more sense. Unfortunately, as I've said, no algorithm yet, so lots of money in it for you if you can find an algorithm that actually does work. Cool. So that's the end of traveling salesman problem, finding an upper lower bound. We are going to practice this and practice a few more examples and past papers. But basically, there's nothing new more to learn. So it's quite nice and short and sweet. Well done.